Okay, so just to wrap up second quantization, I realized the sort of example I gave was kind of bad for the position basis, but so let me just give a cleaner one. Remember, the position basis is based on these pseudo eigenkets, right, of particles located at particular positions. So it could be n of them, however many, and these things are given by 1 over square root of n factorial, and then we introduce these creation annihilation operators for particles at particular locations. So for n particles, there'd be a product of n of these guys, and I'm dropping that spin index because that's a little bit, you could include it, of course. You could like label these with the spin state if you wanted, but I'm not going to do that because not strictly necessary. You can imagine these are spinless bosons or something. But of course, this works for fermions and bosons and any spin that you want. So this is the way we constructed this basis vector. This is a basis vector. This is the moral equivalent of having x, this ket for the single particle. And so then if you want to construct a multi-particle wave function, what you do is you do the inner product between this basis vector and the state that you're interested in. So there's a kind of moral equivalent. Wow, my computer's super laggy today. All right. There's a moral equivalent between this kind of thing, which would be a single particle wave function, right? And the multi-particle version, which is, and let's do this. So this is the example I'm going to do. I'm going to do 2 particles. So you have this basis vector and you dot it with some multi-particle state of 2 particles. This 2 means 2 particles. And remember that in second quantization, the multi-particle states are generated by acting with creation operators for that particular state of a particle. And so, okay, so we can write this basis vector as 1 over square root of 2, and this is the vacuum, and then since this is the bra, we have to turn the psi's to their complex conjugates. So you have psi R1, psi R2, right? And then for this guy, for the state, let's just say we're going to pop in a particle in state I and another one in state J. That's just what we're going to do. And so this thing, and this also has to be normalized by square root of 2, right? That's how we define those multi-particle states. You just pop in using the creation operators, particles, and whatever state you want. You pop those into the vacuum, and there you go. So what is this inner product? Well, okay, it's 1/2 vacuum expectation value of creation annihilation operators. And these are just like the creation annihilation operators for, they're just, so you can do lots of things here. You can expand these size in terms of the basis of AIs, or you can just directly use Wick's theorem to evaluate this vacuum expectation product. And the only thing that you have to know is that when you do the contraction between these annihilation operators and these creation operators, that the contraction gives you a factor of the wave function, because we showed last time that the commutation relation between the annihilation operator in the position basis and a creation operator in whatever state basis you're using is just the wave function of that state. So these could be energy levels, right? You're popping in a particle at a particular energy level, and this commutation relation is the identity times a number, and the number is just the wave function evaluated at that position. So, so you can actually just do Wick's theorem now, and we know that vacuum expectation values are just going to be sums of all the contractions. And there's two contractions. Remember, you contract always the annihilation and the creation operators, because contracting two of these guys will just give you 0 if you do, you know, psi, this is just 0. Similarly, you know, a dagger also gives us 0, because you're popping in two particles and then you're sandwiching with the vacuum, so you don't get any terms left. So the only contractions you get are these two, and also the opposite ones, right, where this psi gets contracted with this guy and this guy gets contracted with that guy. So what do you get? Each of those contractions will just contribute a single factor, will just contribute a wave function. So for this first contraction, you just get psi I R2 times psi j. And these are the wave functions now, psi j R1. And then for the other one, you get these two guys, and it would be plus or minus depending on fermions or bosons, because we require one exchange of operators to flip the, we require one exchange of these operators to make the two contracted guys next to each other. So you'd have a plus or minus for fermions and bosons. And you would just have the opposite, right? You would have psi I, and the psi I is with R1 now. And this psi j is with R2. And this is exactly what we want, right? It's either a symmetric or anti-symmetric combination of wave functions. So it works exactly as advertised. And this is the connection between second quantization, which we looked at during this last bit of identical particle section. And also that's the connection to the first part where we just symmetrized or anti-symmetrized wave functions, right, to get the right particle statistics. So that's the connection. Yeah. Was there a question? Nope. All right. So I just wanted, this is a better example before I did a more sort of general thing where I did a linear combination of these AIs and Js, but I think that's not, you don't have to do a linear combination. You can just say, well, I'm going to look at one particle in state I and another particle in state J, and introduce creation and annihilation operators for that. So, all right, let's see. And we talked about dynamics a little bit last time, but again, you'll practice that on the homework. The dynamics, since the only kind of state we're ever worried about is the vacuum, this is sort of time independent. It doesn't move, so it doesn't evolve. So there's no Schrodinger equation here because everything involves the operators. So what's evolving in time, the dynamics are the operators themselves, the creation annihilation operators. That's what's evolving when you're doing second quantization. So any kind of equation of motion you write down will be for the operators. So you use the Heisenberg picture. So you have a Hamiltonian, which will typically have some form that includes one particle and two particle interactions. You got the one particle interactions, and you've got the two particle interactions. And these, then the operators themselves, the annihilation operators, evolve according to the Heisenberg equation of motion, which is just like the Schrodinger equation, except instead of the Hamiltonian, you have the commutator between the Hamiltonian and the operator. And you can use this as an equation of motion to figure out the dynamics. And of course, you can put it in position space, and you can get an equation of motion for not these annihilation operators, but instead for the field operators. And you introduce a partial derivative here because you know that the field operators will depend on a spatial coordinate, right? So you want to make sure you're indicating this just a partial derivative with respect to time, holding the position coordinate fixed. And this also, you know, obeys the Heisenberg equation of motion. So you take psi and commute it with h. And that gives you, you know, instead of sums over states, you get integrals over coordinates. That's what we did last time. And you can use this equation as a kind of quote unquote Schrodinger equation, but it's not. It's really a Heisenberg equation of motion for the field operator, which what does it do? It annihilates a particle at location r. And unsurprisingly, you can then do like I did in that example, where you can take this equation and you can figure out what happens, or you can take this equation and you can figure out what happens to the multiparticle wave function by sandwiching this equation between by basically, you know, you could effectively rewrite the wave function in terms of creation annihilation operators, and then use the equation of motion to figure out the equation of motion for the multiparticle wave function. So that's something else you can do. So yeah. And then just to briefly mention how about QED. So QED, the reason it's taught sort of first in field theory classes is because it's, you know, the first sort of obvious non-relativistic, it's the first obvious relativistic theory. It's the first theory for which you know, sort of the non-relativistic stuff we do breaks down, right? Because we know, for instance, the energy momentum relationship for a photon is just not, you know, p squared over 2m. That's not the momentum of that's not the energy of a photon. The energy of a photon is, you know, its momentum times the speed of light. So you're forced immediately, when you're dealing with electricity and magnetism, to consider particles that, you know, can't be treated with the usual Hamiltonian that we keep writing down, right? H p squared over 2m plus v of x. This doesn't work for photons. So, and that's the issue. And moreover, single particle quantum mechanics breaks down also when you have relativistic momentum energy relationships. And there's a kind of interesting way to see this. So when you have QM and you add relativity, or, you know, in particular, you do the proper energy momentum relationships that, you know, E squared is p squared c squared plus squared c to the fourth. So once you have the proper energy momentum relationships that obey, you know, special relativity, the entire single particle picture of quantum mechanics sort of breaks down, because there's a kind of funny way to see it. You can think about the time evolution operator for going from between two different locations, x and some initial x naught. And in here, you know, you would put free particle evolution. So you would put e to the minus it over h bar times some free particle Hamiltonian. And if we think about the free particle Hamiltonian, how would we do it? Well, you know, let's imagine that we could, for instance, use this as the energy. So then your free particle Hamiltonian might be something like square root of, you know, p squared c squared plus m squared c to the fourth. And so you can actually try to use this to compute this transition probability amplitude. And what would you find? Well, you would find that, well, you would have to, so this is in the momentum basis because you have the P here. So you have to introduce a completeness relation in here, right? You introduce completeness over momenta. And you could then write this thing as an integral over momentum space, dp 2 pi cubed here. You'd have the wave functions associated with the free particle, which are the plane waves. So you have e to the IP x minus x naught over h bar. That's just from these guys. Then you have the part that actually comes from the Hamiltonian minus IT over h bar, square root of p squared c squared plus m squared c to the fourth. And what you find is you can actually use stationary phase approximation, which we've done. You can actually look at it in the limit where h bar is small, so that these guys are very quickly oscillating. So then what you do is you look for the places where the exponent is slowly varying. So you take these exponents and you differentiate with respect to p, and you find the place where the first derivative vanishes, and you stick that in. And that's some tedious algebra, but you find that this is at least proportional to e to the minus m square root of x squared minus c squared t squared, where x is the absolute value of x minus x naught. So this is after you do the angular integration. You make x minus x naught point along the z-axis, and then you do the integration over the angles of p, and then then you do stationary phase on the magnitude of p. You get this. But look at this. This is very bad in terms of relativity, right? It means that if we look at it, you can get transition probabilities where the distance between your initial and your final position is actually bigger than CT. That's really bad, right? That means that lives outside of the light cone. So if your initial position is here, that means you have some propagation in time t that is actually outside of the light cone. So the time direction outside of the light cone centered at your starting position. So that has to be patched up. You can't have transition probabilities outside of the light cone. That's going to violate. It's going to violate special relativity. Quantum mechanics also, it has to obey special relativity. The probability that, so even with probabilistic quantum stuff where you get the probability of observing a particle in various places, special relativity is true with quantum mechanics as well, so that there's literally zero probability for observing a particle moving outside of its light cone. That's just not possible. And you can see this. So this treatment of and what went wrong here is that we assume that a particle can be described by this kind of funky Hamiltonian that just kind of shoes in the special relativity aspects, right? We're just going to put it in and assume that we can do this kind of square root of this energy momentum relationship and just see what we get if we try that. And if we try that, it gives you results that violate special relativity. So that's a problem. And so the fix is introducing fields. You're actually forced into using quantum field theory instead of single particle quantum mechanics. You kind of become obligated to have to introduce identical particles, multiple identical particles, and using a Fock space with a potentially infinite number of identical particles instead of single particle quantum mechanics. That's a little bit of a hand wavy reason for that, but so it goes. So and that's kind of where QED starts, is to try to understand these energy momentum relationships that are explicitly relativistic. So for a photon, you could try writing down a Hamiltonian, right? What would it look like? Well, there'd be a sum over wave vectors or momenta. And then, of course, you would have to use the kinetic energy for a photon, which is, P times C. And you could then say, okay, these are the energies of a photon, and I'm going to count up the number of photons in both you can use whatever basis you want, either linearly polarized basis or the left and right handed photons, the circular polarized ones. If we do circular polarized, then we would count up the number of circularly polarized photons with momentum k. And these are just the number operators for counting those up. And then we have the ones with right-hand polarization, left and right-handed polarization, right? So these are plus or minus notation here. And these are just the number operators associated with counting up the number of photons there. So that would be a photon Hamiltonian. But of course, this is the momentum basis. And if we wanted to move to the position basis, things get a little bit complicated because, again, of this issue that this momentum relationship is actually, it's very awkward in position space. How would we even write this in position space? It would be something like C h bar square root of minus the gradient squared, be like that, right? That's very awkward. That's not a local term. That's not it's not analytic. It's you can't express it as in a clean way in terms of like derivatives of fields, because there'd be an infinite number because of the square roots. It's very awkward. So you have to fix this. So that's one of the issues that comes up. So it's not enough to just say, well, I'm going to call my creation operator for a photon at location R. Just what I usually do, just the unitary transformation of the momentum basis guy. You can't do this because of this issue with the fact that if you try to write down a Hamiltonian using these guys, you'll run into this issue of having to rewrite this guy. So you have to introduce slightly modified field operators. And those field operators turn out to be the operator versions of the vector potential, as it turns out. Like A, if you remember from E&M. So what happens is that you introduce operators. There's one for the two different kinds of helicities, or two different, or you could do the linear polarizations, the two different circular polarizations. The field operators are in position space. They have a funny normalization, but they look quite similar to what we would naively use, except they're corrected a little bit in order to get rid of this annoying term in the Hamiltonian. They're corrected because we can correct things in momentum space easily by just dividing by 2ek like this. What does this do? This will just divide out by the right factor to get. So there's, that in the Hamiltonian there'll be a product of two of these guys. So when we take a product of two of these guys, we'll get 1 over the energy, and that'll cancel this guy here. So you'll get rid of any of the funky non-local terms by doing this normalization. But these are different operators now, because now it's a different linear combination of the momentum creation operators, right? we have this stuff out front. It's no longer just the thing that we would normally do, this thing. So they're not quite the same thing. They're not like operators that generate a particle, right, at some location. They don't have that interpretation. Anyway, it would be kind of confusing if they did, because, you know, the photon doesn't have a rest frame. So you can't really, there's no field operator, it just pops in a photon at a particular location. And similar thing here, I'm not going to rewrite it. It's the same thing, except these guys are for different helicities. Oh, sorry. So this should be, I guess, dagger. Okay, and so then you can use this. You can use this to rewrite your Hamiltonian, and I'm not going to do that because I do want to talk about supersymmetric quantum mechanics a little bit. But what you find is that let me think a little bit how to say it. Yeah, so if you try to rewrite the Hamiltonian in terms of these operators, what you'll get is in coordinate representation, you actually just get the electromagnetic energy. And there'll be an extra term, which is the ground state energy of, it's the 0 point energy of the electromagnetic field. It'll look like that. These omega k's are just the omega k's of the photons. They'll just be this constant term subtracted off. And these e squareds and b squareds are just going to be derivatives of the vector potential field operator. So B is the curl of A, and E is the time derivative, like that. So the electromagnetic energy comes in, except now it's not like the classical one. E and B are not classical fields, but they're derivatives of the vector potential. And the vector potential is a linear combination of creation or rather annihilation operators for the photon. And all of this you can show is also equal to this, right? Which is just counting up the number of left and right polarized photons at particular momenta, just summing up over all the ones you find. These are just the number operators. So this Hamiltonian is equal to, using this transformation, which I'm not going to go into, is equal to that. And this is a sort of a starting point for sort of quantum approach to electrodynamics. You can then, of course, introduce an electron. That's even more kind of annoying, because now for an electron, you really have problems, because the energy momentum relationship is this guy. So you have to figure out how to fix this up so that you avoid having to write down things like this. Like if you would naively do this, what would you do? You'd say, well, I'm going to count up the number of electrons at some location R, all right? And then I'm going to count up their energy, which apparently is the square root of minus h bar squared, you know, c squared, Nablus, the Laplacian, and like this, right? That would just be a naive expression for the energy. But this is bad because, again, these are non-local things. So you have to do something else. You have to introduce a different description for the electron. Turns out the one that works is if your field operators actually has 4 components in it, and that introduces the Dirac spinner description for an electron. So you can't use a single component thing because you run into this issue of having a very poorly behaved Hamiltonian with non-local terms in it. Good thing about it is infinite derivatives, right? I can like Taylor series expand this square root if I wanted. I get like an infinite number of derivatives. So that's very bad. But you can fix it up, and that's what Dirac did in order to make a relativistic energy that's also local. It has a normal kind of look to it in terms of, you know, a finite number of derivatives, 2 derivatives. So that's, but I don't want to, yeah, that's a topic for a quantum field theory class for sure. Any questions about that? Very hand wavy, but you know. Oh, one last thing I wanted to tie it back to what we did in class. Of course, you can, so now you can do everything with, so remember the path integral. What happened there? We had that you know, quantum mechanical expectation values were connected to classical Lagrangian, and you can do the same thing in field theory, of course, except instead of like particle locations and stuff, we're in the second quantization land where you have multi-particle states, and in particular you have fields. You can consider eigenstates of, say, field operators, and then you could consider transition probabilities between different field configurations. And so that's what the path integral allows you to calculate. It allows you to calculate the expectation value or, you know, the transition probability amplitude between different field configurations, where these things are classical field configurations corresponding to, say, eigenstates of one of your field operators, say like the vector potential or something. And in terms of this, what is this equal to? This is equal to an integral over all now field configurations, phi. This is all the different, instead of integrating over all particle positions or whatnot, we have to now integrate over all fields, all possible fields. And the field is, you know, a function of the coordinates. So it'd be, you know, an integral over all functions of your coordinates. And then the thing is, in here, it's still the action. And you'd have to integrate over both time and space. But it's the integral of some Lagrangian, where now this Lagrangian is a function of the fields. And so that's what field theory is about, is using all the stuff we learned, you know, path integrals, perturbation theory, and so on. But it's in this bigger space, not a Hilbert space of a single particle, but rather a Fock space, meaning an infinite tensor product of Hilbert spaces corresponding to an arbitrary number of identical particles. But we know that those things, that space is described by second quantization. And so the relevant quantities in that space are the creation annihilation operators. And when you're using the position basis, those creation annihilation operators are, you know, field operators. They're size, and they and we can think of those as the fundamental sort of quantum objects. And so then all the stuff we apply, like perturbation theory and so on, just applies to those things. And then for the path integral, for instance, you could think about transition probabilities between different field configurations. So that's kind of how it comes in. There's two, and again, there's like two different approaches to it, right? You can think about it from the particle perspective, right, where you introduce multiple particles and that leads you to the concept of fields. But you could have gone also the other way and said, I'm going to start with something like a theory of electricity and magnetism, which already has fields in it. And then I might say, well, how do I make this quantum mechanical? Well, surely the fields have to become operators because, so we know if you have an observable, like an electric field, then it'll have to become an operator in quantum mechanics. So you could go that way. It's kind of a more natural way to go, I guess. But if you start down the route of single particle quantum mechanics, you also get to the realization eventually that if you try to include special relativity, or if you try to treat like explicitly relativistic particles like photons, you'll right away realize that you need to extend your space beyond just a Hilbert space, but in fact have to introduce the concept of a Fock space and these field operators. So, and you kind of rederive the vector potential in a sense by trying to understand what the quantum mechanics of a photon would be. All right, hopefully that's kind of fun to think about. I know I'm not giving it any justice, but hopefully you get some flavor. Any questions about that? It's hand wavy stuff, but you know, that's sort of my perspective on it, I guess. All right, so last 25 minutes here, I'm going to talk about supersymmetric quantum mechanics. Supersymmetric quantum mechanics, it's not really like real supersymmetry, but it's close. It's actually quite close. And so we're back to single particle land. So we're back to single particle Hilbert space. And in single particle Hilbert space land, what supersymmetric quantum mechanics is, it's a special symmetry of certain kinds of Hamiltonians. And these Hamiltonians are roughly ones which you can take a square root of them. That's a good way to remember what SUSY is for simple quantum mechanics. And the idea is you have some operators, QI operators, and they obey a certain set of commutation relations, just like angular momentum, position momentum, and so on. These obey their own, and these are the following. They obey a set of anti-commutation relations, where if you take two of them, then they generate the Hamiltonian. So it's sort of a little bit like the creation annihilation operators in second quantization, but different. And also their commutation, they commute with the Hamiltonian. So they have these sets of relationships. And these guarantee then that if I look at this equation, right, and I set I is equal to J, right, it means that QI squared is equal to H, right? It's a square root of your Hamiltonian. So any Hamiltonian that can be written as the square of such an operator satisfying these relations is a supersymmetric Hamiltonian. And you can also make some conclusions about this, right? So first of all, these guys are Hermitian operators. Should have said that. It means that any supersymmetric Hamiltonian, since it's the square of a Hermitian operator already, that means its energy levels, right? The only possibility here is that the energy levels are all non-negative, right? You can't, because it's the square of something. So, and also if H acting on some state gives you 0, the only way this is possible is if Qi acting on some state gives you 0. These are equivalent. And you can also define an interesting parity operator. Sigma, which has the following property, that if you take one of these Qi operators and you act with it, then it gives you minus that. You can see what happens with the Hamiltonian under this parity operator. I can introduce the identity here. This is just the identity here. And we know both of these guys give us minus Qi. So this must be Qi squared again. This is H. So the Qi's are odd under this parity operation, and the Hamiltonian is even. And notice that this also means that sigma commutes with the Hamiltonian. What does that mean? It means that we can, our energy levels are can be made simultaneous eigenstates, right, of both H and sigma. So, so that's good. And moreover, we know that if Qi acts on a state of a particular, for a particular eigenvalue of sigma, then will be taken. So Qi will take us from states with sigma plus 1 to states with sigma minus 1. Because if, say, we had an eigenstate of sigma that was, say, minus 1, then if we do sigma q psi, right, then this would be sigma q, sigma minus 1, sigma psi, and this would be minus q, right, because this transformation here gives us a minus q, sigma psi. But if sigma psi is itself minus psi, then the minus signs cancel, and we get q psi. So q psi as a vector has opposite parity as psi. So it flips us back and forth. It's a convenient operator which tells you the parity of your state. And another interesting thing is that there's, because of this, right? Because of this operator, right, that flips us from one parity to another, whenever you have a non-zero energy level, what will happen is that they'll get paired off into pairs that can be with the different parity. So if you have a state with if psi is the energy eigenstate with E bigger than 0, then we know that, of course, there's some Qi squared, which is equal to H. And so this is equal to the identity. So let's see, how should I say this? So there's going to be, right? So this operator, if we act on the space of states with positive energy, right, then the inverse of the Hamiltonian is well defined. And so we have this operator here, which you can think about as Qi over the square root of H, which acts like a projector. That if we operate with this projector twice, right, we get back out the identity. So we can define this kind of this operator, I don't know what you're going to call it, Qi over square root of H, right, where this thing squared is equal to the identity. But we know that when we act with a state with one, we know if we act with a state with one kind of parity by these Qi's, then we'll get a state with the other kind of parity. So there'll be two different states for each non-zero energy level, corresponding to two different parities, and we can jump between the two different kinds using this Qi over square root of H bar. So for all the energy levels that are bigger than 0, they're going to be doubly degenerate with different, parities. And we can jump between these two states by using this Qi over square root of H operator, because it's and it jumps back and forth because we apply it twice, we get back to where we started. So it's yeah, so that's the structure. So any Hamiltonian that's supersymmetric is going to have the structure that it's going to have doubly degenerate excited energy states, at least doubly degenerate, because of this property and the fact that the Qi is acting on anything, Qi acting on a state will flip the parity of the state. And of course, then you might have a ground state. The ground state is special because we know we can't construct this operator if our state has a 0 eigenvalue for H, because then you can't divide by H. You can't, in the energy basis, right? This would be Qi squared over the energy of that state that you're acting on. So E can't be 0. Okay. So that's the structure of it. And of course, the ground state is special because you can't construct the operator there that jumps you between the different kinds of parity states. And so the ground state can actually have degeneracies also, but they might, the states here at 0 energy could have different parities, different sigmas. Could be 1, -1, +1, +1. They don't have to be paired off. Here it's always -1 and 1. They have to be paired off because we know that when we act with this, we move between different parity states. So they're doubly degenerate, at least. You can have other degeneracies too. It's just that we know that these Qi's will take you from a +1 to a -1. So there must be always an even number, an equal number of +1s and -1s because of the existence of this operator. But it's not true of the ground state. And counting up the number of ground states with +1 and -1 gives us an index, which turns out to be also the trace of the parity operator, and this is called the Witten index. But okay, and there's a lot of interesting examples of these kinds of things, but let's construct one that kind of gives you a sense of why this is related to supersymmetry at all, like fermions and bosons and stuff like that. And it's related to your homework because on your homework, you're doing a problem where you're showing that the harmonic oscillator, the structure of that algebra, the harmonic oscillator algebra is analogous to second quantization algebra, right? It's the same creation and annihilation operators. So, okay, let's do the supersymmetric harmonic oscillator. What is it? Well, we have to construct it in such a way that it satisfies the supersymmetry. And the way you do it is you have to actually have two harmonic oscillators. And so the Hamiltonian is, it's going to be a matrix with two different harmonic oscillators in it. And they'll both have the same, and this is in non-dimensional sort of units, they'll both have the kinetic energy and they'll both have the potential energy, quadratic potential. These are the harmonic oscillator potential. So this is times this, an identity, which identity here, an identity here. And then we also need a piece that actually makes it supersymmetric, which is the following. You have to have this kind of thing, 1, 1. All right, so no, we'll just call this 1, I guess, identity. And this is minus the identity, 0, 0. Why do we do this? So, okay, so we need two harmonic oscillators because if we think about the energy levels, right, of two harmonic oscillators, they're going to have the same energy levels. So naively, you would think that one of them would sort of be the odd parity harmonic oscillator and the other one would be the even parity one. But it's not quite so simple to make it satisfy the supersymmetric algebra. You actually have to shift the energy levels of one of these guys up by a single spacing. And then you still, so you move the ground state of one of them up by h bar omega so that the ground state is now sort of up here. And now, since remember, there's an infinite number of energy levels, so these are all the, so there's going to be a single ground state now at 1/2 h bar omega, right? For one of the oscillators, but you shifted the other one up by, so that it's up at the excited state. And so for the rest of them, there's going to, each state of this double oscillator system is going to be doubly degenerate, right? Because there's going to be an energy level in each of the two different harmonic oscillators. So all the excited states are doubly degenerate. And this is what this does actually. It shifts one of the eigenvalues up and the other one down by a relative factor of h bar omega. It actually shifts this one down to 0. That's the -1/2, right? The -1/2 for one of them just shifts the ground state energy of the harmonic oscillator to 0. And this guy gets +1/2, right? So this one gets boosted up to h bar omega. So this is what it really looks like in terms of, you know, the dimensionful units is, this is your full Hamiltonian, right? You have a single ground state energy at 0, and then you have h bar omega, doubly degenerate, 2h bar omega, doubly degenerate, and so on, 3, 4. So that's the Hamiltonian, and you can show that this is equal to, you can introduce operators, psi, which are given by 0 identity, 0, 0, and these will be useful in a moment. And in terms of these operators, our Hamiltonian is equal to minus kinetic plus potential piece. This is the identity part. This guy can be written as 1/2 the commutator between psi and psi dagger. It's just simple matrix algebra. You can show that the commutator of these two guys is just equal to this guy with the identities on the diagonals. And this thing is equal to the anti-commutator of Q and Q dagger, where what is Q? Q is equal to A, which is the annihilation operator for the harmonic oscillator, and psi dagger. And this is, and so what does this Q do? This is the Q that flips us from even parity to odd parity states. And what this does is, you see, it has the, if we think about it in terms of the second quantization, this is a fermionic type operator. Why? Because you can show that it obeys fermionic commutation relations, anti-commutation relations. You can show that these psi's, they obey this anti-commutation relation. And of course, they anti-commute with themselves. You can show that for these guys. So that they have the behavior of fermionic creation annihilation operators. And then we know that A, the lowering operator for the harmonic oscillator, behaves just like a annihilation operator for a boson. So what this Q does is it makes a fermion and it destroys a boson. And what do I mean by that in terms of the harmonic oscillator? So look at these states. What are these states? Well, I can label them as follows, right? I can call my states the following. I could specify the energy level, right, of the energy level that we're at. We're either, you know, in state, in this state, 0, 1, 2, you know, whichever energy level we're at. But that's not enough, because we know that the excited states are doubly degenerate. So we also have to specify which oscillator we're at. And that is, can be thought of as the number of fermions that we have. And the number of fermions that we have is either 0 if you're in this oscillator, or it's 1 and you're talking about states for this oscillator. But it's the same algebra as having a certain number of fermions. Just like the energy level of a harmonic oscillator, the level that you're at has the same algebraic structure as the number of bosons in a particular state, right? Because the raising and lowering operators for a harmonic oscillator take you between, you know, +1 energy level or -1. That's like popping in a boson or popping out a boson. So that helps you. That's on the homework. You'll study that. And it's this funny double oscillator, Hamiltonian, introduces the possibility of a fermionic kind of degree of freedom that tells you which harmonic oscillator you're on. But you can think of it as a kind of particle. And so what does this Q do, right? It takes makes a fermion and destroys a boson. So it moves you from one harmonic oscillator to the other one and pops you down a single energy level. And the fact that we sort of yeah, so it's a sort of cute example of where supersymmetric quantum mechanics is at least sort of lightly connected to real supersymmetry. I mean, real supersymmetry is a symmetry between fermions and bosons. But that exists here too. There's, you know, and in real supersymmetry, there's an operator that also takes you between, a particle and its superpartner, which, takes you from a boson to a fermion. There's an analogous thing in the field theory of the Q operator that does that. But here it does that. It takes you from a fermion to or rather from a boson to a fermion. Q dagger would do the opposite, right? So yeah, kind of interesting. But you now have all the tools to sort of play around with this. I mean, this is just our, two harmonic oscillators. Really not much to it. The entire space of states, right? The ladder for one and the ladder for the other. They're just shifted a little bit relative to each other by this term. And so the full space of states, and you can play around with these commutation relations to get some idea of how the supersymmetric algebra works. It's kind of fun. The other place where this comes up is, in quantum mechanics, supersymmetric things, is in the WKB approximation. So that's also kind of interesting topic that we sort of won't be able to get to. But I wanted to give you at least some flavor of this. Oh, by the way, so just to usually so this Q and Q dagger, I didn't really connect this to the QIs. So I should have said this. So the number of QIs tells you what it gives you. Number of I's that you have is the N of your supersymmetry. And for the harmonic oscillator, it's really N equals 2. So there's actually two QIs, Q1 and Q2. And I just wrote these Qs into Q daggers. What this is all about is Q is equal to 1/2 Q1 plus I Q2, and Q dagger is equal to 1/2 Q2 minus I Q2. And in terms of these operators, you can show that your Hamiltonian has to equal the anti-commutator of Q and Q dagger, which is still equal to what I said before, right? The QI squared. Is just sort of rewritten in a slightly different way. So I didn't do Q1, Q2. Instead, I used these Q and Q dagger guys. Yeah, and they have a slightly different algebra than the guys, the Q1s, Q2s, but they do also anti-commute. So this is another SUSY algebra. Another expression for it, another way to write it. Let's see, what else? Any questions about it? So again, to summarize, what SUSY is just a special symmetry of certain Hamiltonians. And roughly speaking, it's Hamiltonians for which you can take their square root, that they're equal to the square of something. And so in your mind, I mean, you should sort of think that, well, if something is the square of something, then there are two square roots that I can take, right? Like the plus or minus square roots. So that's where so for Hamiltonians of that type, they'll actually have doubly degenerate excited states. And in a very loose manner of speaking, that degeneracy, right, going from one kind of parity. The other kind of parity, roughly speaking, is what happens when you change, quote unquote, a boson to a fermion and vice versa. It's jumping between these two different kinds of jumping between the two different degenerate states. And you can work this all out explicitly by looking at this funny harmonic oscillator where you shift one of the ground states to 0 and the other one up by a half omega h bar omega. So you have this really nice setup of doubly degenerate excited states in a single ground state. And then you can construct the analog of the Q and Q dagger operators, the supersymmetric operators, and sort of figure out what the supersymmetry looks like for this example. And I think it's a very nice example because it's sort of easy to understand because we know the harmonic oscillator, but at the same time, it introduces some of these funny anti-commutation relations associated with the supersymmetric algebra. But if you look up in, what SUSY looks like in terms of the commutation, super algebra, you'll see that the operators obey, basically these same kind of commutation and anti-commutation relations. Of course, where it gets interesting is that they also have, they have particular commutation relations with momentum and position and stuff. So that's where the whole actual fermion and boson thing comes in when you actually start thinking about, particles instead of just more abstractly with these energy levels of the harmonic oscillator.